Okay. Morning, everyone. So let's get started. This is our last lecture in this semester. Oops. I'm not gonna do this one first. It's really bad. Just give me 1 second. I don't know what happens here. All right. Okay. Let's continue. So here's the agenda of today. First, we're gonna give a quick review for the final exam. We're not really helping you to walk through every slide, but we just want to share some advice about efficient review. We don't want to take too much of your time because I know you might have to deal with quite a few final exams, project dues, right, in the next week or two, right? So we just want to tell you like, okay, you can review in this way, and it was quick and efficient and should be sufficient. And then we'll talk about in the practical usage, we'll apply machine learning methods or develop machine learning strategies, what kind of common tricks you should consider. Okay, so first final review, final exam. We have posted the final exam detail on our course website. If you have noticed, like we posted a long time ago. So here we just emphasize the time. Again, it's on next Friday, December 15th, and from 8 a.m. to 10 a.m. So it's pretty early. But this was scheduled by the university, not by me. So please please bear with us. So the good thing is that our exam will be completely online. This is on Canvas. So you will see that there will be in the exam quiz section, there will be a final exam which can be opened at that time. So from today, we're gonna keep reminding you our final exam schedule, and to make sure that no one is gonna miss the final exam. Right? And then on Friday, next Friday morning, we'll send another reminder email to ask you guys to log into Canvas and take the exam. So here we just tell you, like, go to quizzes section. Okay? So here's the policy of final exam. First, because it's online, right? No one is gonna watch you at the back, right? So it is open book, an open website. So it just means that if you have any problem, you can just search for the book and search for the slides, right? But do not search or post questions online. So basically, please do not post some questions on Stack Overflow and the Q&A or in Quora, these Q&A websites, right? You can search the answers from website, but mostly you won't be able to find the answers, right? But don't try to post the questions on that and waiting for others respond. That's not allowed. And what are the question types? Right? I guess this is most of you will be concerned, right? So the majority of questions will be like single and multiple choices. So he's like, okay, I will tell you, okay, the following describes SVM classifiers, and you just mark up which statements are true, right? For example, SVM is linear classifier, SVM is nonlinear classifier, SVM follows risk regularized risk minimization principle, right? So it will be several statements, and you can check you can check which statements are correct. This one example, right? The other example might be like a neural network. The backpropagation is what's the description? What kind of understanding of backpropagation is correct, right? And we list a bunch of description, ask you to choose which ones are correct. Okay? And the second type of problems are text description. So basically, we're gonna ask some questions and ask you to write down your understanding. Like, for example, we might ask you, can you tell me how SVM can fulfill nonlinear classification? Right? You don't need to write down any formula. You don't need to write down any math, but you can say, okay, we're gonna convert it into a dual form, and then we inject kernel trig, and they were essentially performing linear classification in a high dimensional map to feature space, right? So just say something like that, and to show that you really understand what we want, right? And because this is the problems are random pickup from a pretty large dictionary, so it is possible that many of you have to address a slightly different set of problems. So that's common. Okay, so how many? So any question regarding the final exam schedule and policy? Okay, yeah, just to make sure join the exam on time, right? It's hard to schedule another makeup exam if you miss it. Right? Okay, coverage. It will ask questions regarding what I have discussed throughout the whole semester. I won't be restricted to say neural networks or SVM, which we discussed after the fall break, right? I might ask decision trees, right? So they may ask, we might ask, okay, are decision trees linear classifiers or nonlinear classifiers? Just tell me. Right? So how do you review, right? How do you prepare for this exam, right? So first of all, don't be stressed for this, right? Because this is a course is not hard, honestly. is much easier than the homework problems you have seen. So if you're okay with your homework problems, you won't feel bad for this final exam problems. It's just a quick check, and also kind of push you to give a systematic review of what you have discussed, right? It's not trying to ruin your final grade, right? So don't worry about that. But we do suggest you to review the lecture slides and carefully go through the paper problems in the homework assignments. Right? That won't take too much time, but will be very helpful because you don't need to memorize anything. But once you have gone through those slides and problems, and we want to search related content, it'll be faster. So any question? Great. So now we have a quick, let us quickly look at what we have discussed throughout this semester, right? So we first gave a formal definition about machine learning, right? And then under that framework, which we specifically we mean to the supervised learning framework, right? And under that big framework, we have discussed a variety of models and algorithms, right? And we also discussed in more abstract level, what are the learning principles? Like for example, the perceptron, they're mistake driven, right? For linear regression, they're minimizing some training loss, right? And this can be summarized as a so-called empirical risk minimization, right? And then later we talk about SVM, we talk about, okay, the generalization error bound is not only determined by the training data fitting, but also determined by some penalty over the model complexity, right? So we call it, okay, you need to, we say you need to add some regularizer over your model, right? Over your training procedure. So we call it regularized risk minimization principle, right? And also we introduced the basic ideas of computational learning theory, right? So in theory, if we want to characterize some machine learning model is good or not, right? We should use some probabilistic statement, right? Why? Why shall we use probabilistic statement? Be careful, this might be some questions in the final exam. Remember, when we talk about, like when we define PAC learnability, right? Probably approximately correctness, right? What we said is, okay, with high probability, right? The algorithm can achieve the generalization error at least at most 1 minus epsilon, something like that, right? This is called a probabilistic statement, right? So why can't we say, okay, my algorithm will guarantee 95% accuracy? Yeah, overfitting is one issue, right? But let us just get rid of overfitting. Like consider like even if your data is noiseless, don't have any noise, you can't say deterministic guarantee. Why? No one remember? We emphasize this, right? During our class. That's because the performance of our model not only depends on algorithm, it also depends on the data. The data is random. Right? The training data is sampled from some unknown, highly complicated data distribution in real world, right? You don't know what the distribution form is, right? You only need to pray that, okay, this time the data set I collected is good, right? I pray that I won't see very bad quality sample from that data distribution, right? But performance highly dependent on the quality of data, right? It is likely that you got very good performance because your data quality is good, but next time we'll have another data set which is sampled not very good, right? And performance bad, right? That's why we can always say probabilistic statement, right? Because you have to consider the randomness from the data. just be careful. Like just be careful the points we have emphasized during our discussion in the class, right? And also we spent most of time, I guess, about the implementation and practice, right? So that was reflected by our homework assignments, programming portions, right? We asked you guys to implement those models and algorithms from scratch and test it on some small but real world data set to show your implementation is working, right? We believe only in that way you can show that you really understand algorithm. You really know how to apply your algorithm. Okay, so what is machine learning? Learning essentially is ability to generalize. You must gain some kind of ability to generalize from the teaching examples to some like wild word. There you could see like you have a learning ability. Otherwise, it's just memorizing. It's not, you're not learning. Right? So Tom Michel gave a formal definition of learning is a computer program is set to learn from experience E with respect to some class of task T under some performance measure P if its performance at tasks in T as measured by P improves with experience E, right? So I suggest you guys to read through this a little bit lengthy definition several times to gain the sense, right? So just basement is under some particular metric, under some particular task family with more data added, you're gonna improve your performance, right? It just reflects that okay, you should generalize better and better when you have being taught with more and more data. Then the most important framework, which we have discussed on this class, is called supervised learning. Right? So the basic setting is that okay, we got instance space, which consists of a possible set of examples you might want to predict, you want to regress, you want to classify, right? And we have a label space, which represents what kind of particular task you want. Like if you want to do binary classification, then your label space is just binary. If you want to do multi-class classification, like you want to classify if you want to tag the news document, or it could be entertainment, it could be political, it could be military, it could be finance, all kinds of stuff, right? It can be multiple. It might have multiple tags, right? So those tags are those tags constitute Y, right? The label space. So the underlying assumption is that we're gonna assume there is some ground truth function, which maps from the instance space to the label space, right? And this is this ground truth function, we call it target function. We want to learn to approximate this target function from data. Right? So basically, the learning is that we're gonna collect a set of examples, which we call training examples, right? In supervised learning framework, that means each training example is a pair of instance and the label generated by the target function, right? So we use this set of labeled training data to drive our machine learning algorithm, right? To search over some kind of hypothesis space, right? You want to find out among this hypothesis space, which one might be the best approximation to the target function, right? So here we use approximation because in most cases, you actually don't know whether your target function is inside your hypothesis space or not, right? What you can expect realistically is just to find a good approximation rather than you really find target function, right? So a learning algorithm should report or should give you a learn function G, which is also mapping from instance space X and to the label space Y, right? So this is called a hypothesis, right? So you can imagine the searching is over a hypothesis space, which contains many candidate functions. You're going to pick up one of them, right, as your learning result. If we adjust this learning protocol, right, by assuming some labels are missing, this is called semi-supervised learning, right? Portion of the examples don't have labels, and portion of the examples have. This is called semi-supervised learning. If you get rid of get rid of all the labels. Like, you only have like instances. This is called unsupervised learning. But our focus throughout the semester is the variety of supervised learning models, right? The reason is once you know supervised learning, it's very straightforward to transit to unsupervised learning or semi-supervised learning. Like nothing non-trivial. It's very, very, very simple. Right? So here a list of the machine learning models, the algorithm I've discussed. Right? We start with decision trees, not because it's simple, because it's intuitive. Right? It kind of reflects how human beings are making decisions according to variables, right? So you're kind of building a hierarchical partitions of data set according to each variable's ability to discriminate, right? And then you just hierarchically partition them until you reach at enough finer level. So based on those combination of the variables, you're able to predict. You're able to make this decision, right? So then we have discussed a very efficient way to construct such a tree, right? So from Occam's razor's principle, we should find out the decision tree we have, which has the smallest size, right? Because we favor the simplest model under the same fitting to the data, right? That's the so-called Occam's razor's principle, right? Don't forget to review what is Occam's razor's principle. That might be the question you want to ask, that we want to ask during the final exam, right? But if you're really to want to find a globally minimum decision trees, that will be hard. That's why we use that greedy search approach, right? And this is called ID3 algorithm, right? And then we talk about the several ways to find out the best attributes or features at each step, including information gain, majority error, and Gini index, right? And then after decision trees, we'll talk about ensemble learning, right? Basically, how can we derive a very powerful machine learning model from a set of very weak classifiers, right? Decision tree is one such a weak classifier. But here, when we say weak classifier, means that you're going to restrict the size of decision tree, right? For example, in boosting, the most common use is called decision stump, right? Just one level decision tree with single variable, right? And then we'll talk about another way of doing ensemble, which is called random forest, right? And you should know why random forest or like other ensemble approaches are working. Right? We have some mathematical derivation to show that. You see that the generalization error is decomposed as a bias term and a variance term, right? And doing ensemble means that you fully train a decision tree and you want to grow it as large as possible. Means that you won't change the bias term, but by average a set of classifiers or regressors together, you're gonna largely reduce the variance. Right? That's why the ensemble works. And least mean square for linear regression, right? Then after that we start talking about the linear models. We start with least mean square method. From least mean square method, we introduce the concept called loss, right? Loss represents how well we fit data, and we'll talk about how do we conduct stochastic gradient descent, right? And then we talk about our first linear classifier algorithms, which is called perceptron, which I'm not gonna repeat again. Then we switch. Then we move on to support vector machine, right? We spent quite a few lectures talking about all the mathematical details about support vector machines, right? And support vector machines, you should know, it was motivated by computational learning theory. Right? From the computational learning theory, we can derive some generalization error bound, right? From the generalization error bound, and when we look at the linear classifiers family, right, we found that the model complexity actually was governed by the so-called margin, right? So that means if I want to tighten the bound, we should maximize margin, right? So don't forget such kind of connection, right? And the justification, and then we derive SVM, and then we have a bunch of tricks to. So at the beginning, we have like a two-level optimization problem, right? And then we make some simplification on that by leveraging linear classifiers property. That is, if you skew your model parameters by arbitrary positive constant factor, it doesn't change. Right? So we can convert a two-level optimization into one-level optimization with constraints. Right? Right? If you kind of like feel weak about this, so don't forget to look back at the slides, right? And then we'll talk about how do we generalize to SVM to nonlinear SVMs. We'll talk about the dual form, right? We talk about KKT conditions. We talk about during the dual form, how do we replace the dot product between the feature vectors by the kernel function? That means we implicitly performing some nonlinear feature mapping, and then do the learning, right? And also don't forget what's the meaning of support vectors, right? Why we call which training examples are called support vectors. Remember the final weight vector actually is the linear combination of the training examples, right? And some training examples, their weight are simply 0, right? They're not support vectors. It turns out that your optimal weight vector training from SVM is only determined by a linear combination of small subset of training examples, right? Those training examples are called support vectors, right? So don't forget looking at those, right? And we can see that we can use kernel trick to make SVM to be nonlinear. We can also apply kernel trick to make perception to be nonlinear. Then we switch to another way to construct nonlinear models. We call artificial neural nets, right? Artificial neural nets are not constructed by extending existing linear classifiers. It was constructed from scratch, right? So by stacking and connecting a set of basic blocks, which we call linear threshold units, we can construct a highly nonlinear model. It's called artificial neural nets, right? And the most important thing about artificial neural nets is how we efficiently train a model, right? Because model neural networks, it's not surprising to say you've got 2 million parameters. And we need a way to efficiently capture the gradient, right? So we use backpropagation. Backpropagation is a very smart leverage of the chain rule. That's it, right? And then we talk about Bayesian learning, right? We talk about the two notions of Bayesian learning. One is that, okay, I'm gonna just learn a probabilistic concept, meaning that I'm gonna predict the probability you have positive label, right? This is called logistic regression, right? And you can also formulate the whole learning objective as a probabilistic model, which we call naive Bayes, right? That's the lecture we have discussed last on this Tuesday, right? And those machine learning models can be roughly characterized as linear and nonlinear models. So linear models include least mean square method, perception, SVM, logistic regression, right? And nonlinear models include kernel methods, right? If you inject kernel methods to these linear models, they become nonlinear neural networks and decision trees, right? So don't forget, decision trees are highly nonlinear models. It's not linear models, right? And it boosts in random forest. And we can also categorize machine learning models into probabilistic and non-probabilistic, right? So probabilistic learning we have discussed recently, including logistic regression and naive Bayes, right? But non-probabilistic models are like neural networks, decision trees, SVM perception, and so on, right? Those are non-probabilistic models all have probabilistic versions, right? Those are not topic of our class, right? And we hope you also got some chance to take a look at basic concepts and conclusions in computational learning theory, right? What is PAC learning framework? What is PAC learnability, right? PAC learnability just gives us a criterion telling which type of algorithms are good, which types of algorithms are not, right? It's mainly from the sample complexity, right? If you want to learn some hypothesis which satisfy some performance criteria, like meaning is with high probability to get some error less than some epsilon, right? If you can observe that to satisfy such kind of learning performance, the number of examples won't change exponentially. Instead, it changes or it grows polynomially. Then it's called PAC learnable. model, right? We can see, okay, this algorithm, you could conclude that this algorithm can pack learn this type of target functions, right? And then we'll talk about sample complexity bound, right? So what's the generalization error bound? Right? Those are based on consistent learner and agnostic learner, right? Of course, agnostic learner is more important, is closer to the reality, right? Agnostic learning doesn't assume that your target function is really inside your hypothesis space. It could be outside hypothesis space, right? And in that case, how do you bound the generalization error of your learned hypothesis, right? And where is VC dimension, right? Why do we introduce VC dimension? Why do we introduce VC dimension? Any thought? No one remember it? Yes, exactly, right? So during our discussion about sample complexity bound, we're assuming your hypothesis space is finite. You see it in your bound, it contains the size of hypothesis space, which represents the complexity of the model, right? After all, the number of parameters, number of samples you need is partly up to the complexity of the model, right? Which are naturally reflected by the size of hypothesis space if your hypothesis space is finite, right? What if your hypothesis space is infinite? Right? Then your sample complexity bound will become meaningless, right? In that case, we have to introduce an alternative measure, which is called VC dimension. Okay? So please do not forget what's the definition of VC dimension and what's the general procedure to find VC dimension for a class of classifiers, right? And how is the large margin principle derived by the generalization error bound? I guess let's circle back to what I have discussed about SVM, right? How SVM was invented, right? And also the more abstractive principles of learning machine learning models, right? So empirical risk minimization are mainly trying to fit data, right? It's trying to fit data as good as possible. But if your data is not noisy, the data is sparse, then this empirical risk minimization can overfit, right? Overfit data and also hurt its performance, right? So that's why in practice, we often introduce some regularizer to penalize the complexity of the model. So this is called regularized risk, regularized empirical risk minimization, right? Typical example includes SVM and map estimation for logistic regression. Right? If you could remember, at the end of last lecture, we talked about how do we address the issue of naive Bayes classifier, right? If you don't observe some data points, right, you might have zero probability. Right? That's the issue, right? So if you can assign some prior over the parameters of naive Bayes classifier, you can address that problem, right? And from Bayesian perspective or probabilistic perspective, maximum A posterior and maximum likelihood estimation, right? They're all learning principles actually connect back to the regularized empirical risk minimization and empirical risk minimization principles. Right? And from learning itself, right, we talk about gradient descent and stochastic gradient descent, right? We should be aware of the advantages and disadvantages of the two, right? Although I emphasize that in the big data scenarios, the stochastic gradient descent is always more favorable choice, right? You need to know what's the benefit of gradient descent. Why the gradient descent is not favored in a scenario of big data, right? Practice, right? How do you select hyperparameters, right? Usually you cannot optimize hyperparameters along with other model parameters. Like in SVM objective, how do you optimize the constant C, which tells you how much importance your interloss is, right? You can't do that because if you minimize that, your C will be reduced to zero. And that gives you that will give you nonsense results, right? So usually we're gonna extract a portion of the data set as a held out data set to evaluate its performance. Or we can do some cross-validation. That's the most commonly used way to select hyperparameters. Okay. here are the review suggestions, right? We just emphasize again. Go through all the lecture slides, understand the details, right? Go through all the homework problems you have worked, but you don't need to go through program problems, right? And good luck to your final exam. So any questions so far? No, we'll now release that. Yeah. So I guess from the TA's grading feedback, you know if you have some problems, if you have some mistakes, you will know what are the problems. The reason we don't release the homework assignments answers is because we don't want them to spread to next year's. I've seen such kind of disclosure, unexpected disclosure all the time. So we cannot do that. Okay. The remaining task for today's lecture is to share some practical advice for building machine learning applications. I think that will be more important and more interesting to you guys in a long horizon, right? So we're gonna discuss in three aspects. So first, how in a practical scenario, like how to diagnose your learning algorithm, right? So I often see students complain that, okay, this doesn't work, right? This even for toy project, right? Even for simple research project. I'm not saying simple by means that you don't need to have some tied to other different components, right? But in that case, you often see your learning always doesn't work, right? Not to mention, like in practice, like if you come to Amazon, come to Google, your machine learning components will just be one small part of the giant system, right? And when things turn out to be working, right, you need to figure out what is the problem, right? Now, how do we interact with other components to find a faithful conclusion that, okay, this is because this part of your algorithm development is wrong and doesn't fit the needs, so it doesn't work well, right? So we need to have some kind of strategy to help us efficiently diagnose our problem. And error analysis. Once you figure out the problem, right, you need to know what's the problem, which causes the problem, right? It might be because your model is too complicated or too simple, right? It might be because the learning objective you define is wrong. Right? Always possible, but how can we do that, right? And third one is that how we inject machine learning into your task. So we talk about two ways of doing that, right? One is more linear, which is not favored in practice. The other is like big dirty job, which sounds like not very elegant, but that is the realistic way of doing machine learning development in industry or in real world. Okay, first, diagnostic of your learning algorithm, right? So suppose you train SVM or a logistic regression for spam email detection, right? You obviously follow the best practices for finding the hyperparameters like cross-validation, like piled-out tests, right? But it only got 75% accuracy on some big test data set, right? Now the question is, what can you do to improve it? And here we're assuming that there are no bugs in your code. Like we're not talking about if your code has some bugs, right? It's not. This is a software engineering problem. It's not our machine learning problem, right? So in general, there could be several ways to improve the model. Right? So the most obvious way is to add more training data. It's likely that because you don't have enough training data, right, the model performance cannot improve, right? Or the design model. Here for SVM or for logistic regression, the ideas might be just to consider whether features are effective enough, right? We probably can use more features or use fewer features or construct other features. This is from model design perspective, right? And from the training perspective, I mean, from our algorithm perspective, we might consider run for more iterations. For example, if you just run 100 iterations, the model might not converge, so the performance is bad. So I may consider run for 500 iterations or even 1,000 iterations, right? Or I use a different optimization algorithm. For example, if I use LBFGS, I found it doesn't work, so I should change to stochastic gradient descent like a DAM, right? Or I use a different classifier. That means like a kind of like a change to a completely different model, right? I can switch from SVM to artificial neural nets. Or during the loss function, I play with some regularization. I add some L2 regularization or add some L1 regularization and so on. However, if you just randomly or blindly combine all those techniques and tricks, you soon mess up. It's very tedious. You're prone to errors, and also you're very easy to get lost. Right? You don't know what happens. So want to make the debugging process more systematic, right? To help you better understand what kind of factors cause the behaviors of the algorithm, and so that you can choose an efficient and smarter way to improve your model rather than just blindly shot, right? Blindly shoot, right? So first to diagnose, right? The reason that causes your model fail or unsatisfactory there are not too much reasons for that. Right? We can roughly categorize reasons into 4 aspects. First, your model is overfitting. Right? That means you got your model is overcomplicated, right? And you kind of overfit data, and your data contains a lot of noises. Right? That means okay, you have in your generalization error, it contains too much variance, right? High variance of the model. Right? The second possible problem could be underfit. Underfit means that okay, your model is not powerful enough, expressive enough to capture those complicated shape of your particle function. For example, for a highly nonlinear function, you use a linear regression or linear classifier to learn it, you won't expect super high prediction accuracy, right? In that case, that means your model has high bias, right? The third one can be reduced to the optimization perspective. Right? Your learning does not converge, or your learning does not converge to the right place. And fourth aspect actually goes back to the beginning of your model design. Are you marrying the right thing? Right? Perhaps your loss function design is wrong. Or when you test the performance of a model, you're picking the wrong measure. That is not uncommon, especially in practice. Due to the specific application, you have to adjust the commonly used measure accordingly. It's not just use like root mean square error or prediction accuracy. Those might fail in your specific application. You have to design your own error metric, right? And also you have to convince the users, friends, or colleagues that your proposed measurement is right for application. That's very important. Okay, so let us talk about how do we detect the true reasons, right? We got 4 possible reasons, right? And we need to we just need to check the failure of your model might belong to any of those reasons, right? Or a combination of them, right? So first, what's the behavior of overfitting? If your model overfits the data, right? How can we see it? Yes, exactly, right? Exactly. Right? So the typical behavior of overfitting is that the training accuracy is much higher than the test accuracy, right? So that means the model explains the training data very well, but poor in generalization. That's probably because your model kind of also fits the noises in the data, right? And then you're fitting will be very bad to some unseen new examples, right? And what's the behavior of underfitting? If your model is too simple, right? Then how can you see that? For example, target function is like something like this, right? It's very vivid. But now you're gonna use a linear regression to learn that, right? So what will happen? What will be the training error like? What will be the test accuracy like? Yeah, both accuracies are very low, right? Because your model is too simple, it cannot fit data well, right? You don't expect your training accuracy is high, right? Meanwhile, it won't work well for the test examples. So now if we can look at the learning curves, right? Meaning that when you increase the size of training data, you want to say what's the gap between the test error and the training error, we can conclude whether you're overfitting, underfitting, right? For the overfitting issue, right? You'll see that there's a big gap between the training and test error, right? And although with the growth of the training data, their gap is getting smaller and smaller, but there's still like big difference, right? That's the typical behavior of the overfitting, right? But for underfitting, you see that the training error and test error are close, much closer. Right? I'm not saying like they will be exactly the same, but it's much closer. However, both the training and test error are much larger. Then it's typically underfitting. So now let us see if we can conclude that our model is overfitting or underfitting, then what kind of strategies can we use to overcome the problem, right? So first, for underfitting, that means your model is not expressive enough, right? We can use more features, right, to increase the model complexity. Right? Or we can construct other features, right, to better capture the relationship between the input and output, right? Or we might use a different classifier, right? Right now we use linear classifier, but maybe it's too simple. Now let us use kernel method, right? Or maybe we use neural networks. Yes, that's why you can see this, right? You can see this. So you can see see this. When you grow with more and more training data, the gap between the test error and training error is gonna still decrease. Why? Because you have a lot of data, and you have a lot of data. Then even you want to overfit the training data, it becomes much harder, right? If you only have one example, right, have some kind of noises, it's very easy to overfit by a giant neural network, right? But now you have like 1 billion training examples, right? If you are considering noises, there's so much noises. Even 1 billion, even neural network with 1 million neurons won't be able to fit exactly every noise, right? So that's why in the modern applications, like for neural networks, people try to use big data to address the overfitting issue. Right? And you see that almost all the state-of-art models are trained on big data, like ChatGPT, like diffusion models, right? They're on the big data, and even you are not able to train a ChatGPT model by yourself, right? No, that won't address the gap. Yeah. If you want to address the gap, okay, that's one way. The other way is actually is avoid overfitting. we have discussed previously. It's called early stopping. So that means you won't train 1,000 iterations until you completely fit the data. You just stop in the middle. That's another effective way of doing this. Other questions? Great. So we'll talk about if your model is too simple, what kind of strategies can we take to overcome the problem, right? Oh, however, if your model is overfitting, right? As we just mentioned, right? This is the most it's the simplest way, right? As long as you can collect more data, throw more data in, right? You can leave it overfitting, or you can try to reduce the model complexity, like using fewer features, or replace the current features by other features, right? Or play with some regularization, right? Like SVM, you add some L2 regularization or some other regularizations. For example, in the neural network, people are trying to add some L1 regularization to literally sparsify those weights, meaning that many weights are prone to be zero. That's another way to reduce the complexity of the model, right? So we talk about the strategies to discover overfitting, underfitting, and the strategies to address them. Right? So next we'll talk about how do we see if you're learning, the optimization of your learning algorithm is problematic. This can be observed or detected by looking at the optimization behavior, right? So if you look at how your objective function, the training objective function varies along with the number of iterations, right? You could say whether your training or optimization converges into right place. So usually if you see your learning curve becomes flat at the end, then we could say, okay, your learning kind of converge, right? But if you stop here, right, there's obviously a trend to go down, right? But you stop here, that means your learning doesn't converge, right? In that case, you might need to increase the number of training iterations in your learning algorithm. But this observation might not always be informative. For example, you might observe your learning behavior, the optimization behavior is like this, right? So at this point, like you could see, like, okay, the changing, the decreasing of your loss is still going on, but it's much slower, right? You couldn't say, okay, you converge, right? But probably at this stage, you have already learned a set of good parameters, right? So that's why in practice, you might just look at, okay, if you can find a place where if it's not flat, it's okay, but it's slowly changing, then at least the training of your model is not problematic. Okay. However, if you see some learning, some optimization behaviors like this, okay, maybe that kind of like fluctuate dramatically, then there must be something wrong in your learning procedure, right? This might be more obvious when you set wrong step size in the stochastic gradient descent. Right? In the stochastic gradient descent, because every time you're going to use some stochastic gradient, not the exact gradient, to optimize the learning objective, so your learning curve won't be smooth, right? It could be some kind of perturbating, right? But eventually you will see some kind of same trend as you use the exact gradient descent. You see the trend that they're converged to something, right? However, if your learning curve is kind of jumping up and down around very fiercely, then that means your learning schedule is problematic, right? It's very likely that your step size is too large. And the skew of your stochastic gradient is too large. So kind of like drastically change the objective function value in just a few steps. Right? That's not favorable. Right? Then you need to tune the optimization parameters accordingly. Any question? Okay. So that's the strategy, right? If we find the learning behavior is problematic, you should track the objective and look at their convergence in the right way. Okay, so the last thing about the diagnosis we want to talk about is how do you measure the right thing, right? And the measurement is just important quantitative metric, right? Telling us how well your learning algorithm is done for the job. Right? And accuracy of the prediction is the most common used measurement, but as we just mentioned, it is not always the most most appropriate, right? For example, if your data set is unbalanced, right? Then if you use prediction accuracy, that could be misleading. Like for example, you got 1,000 positive examples, only one negative example, right? And I can construct a stupid classifier, predict every example to be positive. Then my prediction accuracy is 99.9% accuracy. Seems awesome, right? But actually it's a useless classifier. Right? And actually unbalanced label data set are very, very common in practice. Like for example, in online advertising, right? So imagine you have show advertisements on millions of users every day, right? How many advertisements will be clicked? Right? Maybe less than 1%, less than 0.1%. Right? This is a highly unbalanced data set. If you want to build up a click model, you want to predict, given this advertisement on the web page, will the user be interested to click, right? Of course, you cannot just use accuracy to drive your classifier, the learning of a classifier, right? So for the unbalanced labels, right, then we need to measure some label-specific precision, like recall and like precision recall and F measure. Right? Precision for label is just among examples that are predicted with label, what is fraction correct. Recall is among examples with a given ground truth label with fraction are correct. So you don't need to memorize what's the exact definition of precision recall, but just keep in mind when you have unbalanced labels, what other metrics should we use, right? Not just global accuracy, right? Also, the F measure is harmonic mean of precision recall. Those are very heavily used in the information retrieval area. Okay. Now I have discussed, we have finished discussion about how do we diagnose our learning algorithm, right? Next, we're going to look at error analysis. So this is about like, if your system consists of several machine learning models, not just one single model, how do you detect which component is problematic, right? If your overall performance is not satisfactory, right? So in our class, you see your whole world is this ML code, right? But in practice, this is where ML code stays in, right? Actually, inside the giant system, which consists a lot of components, right? And the machine learning component is just one component, right? And you have to be integrated into a big pipeline, and perhaps including data feature extraction, data verification, and analysis, do all kinds of stuff, right? And then you generate output, right? That means, in general, machine learning plays a small role in a larger application. All the previous steps, like pre-processing, feature extraction, and data transformations, are all important to machine learning. Okay? So those are something we have never talked about throughout the class, but you will know them during your during real world applications, right? So then our question is that, okay, when machine learning, your specific machine learning model, SVM, artificial neural nets is integrated into a big system, into a long pipeline, right? How much do each of these contribute to the final error? Right? So we need to analyze those errors. We want to explain why a system is not performing perfectly. Okay? So here we give an example, right? A typical text processing pipeline, right? So I got a piece of text, maybe just news document, maybe several web pages, right? I want to first do the words extraction, right? I just do the post stemming. I just ignore their if it's singular or plural or past tense or future tense or past participant, all those kind of stuff. I would just convert into the same form, right? And then I do parts of speech tagging, right? And throughout the parts speech of tagging, I can do some semantic tagging semantic tagging, which is called tree parsing, right? We parse the whole every sentences into a tree, right? Semantic tree, right? And you extract the features from your parse trees, from your part of speech, from the words, and even from the text. You extract all useful information from the bottom level to the higher level, from the individual words level to some more abstract semantic level. You want to integrate this information into some machine learning applications. For example, you want to predict whether people like your product from the reviews, right? You want to predict whether people are in favor of presidency candidate, right? You are in favor of Joe Biden, or I don't know who will be a Republican candidate, right? And you want to use that to give you some advice on how kind of campaign strategies we should use, right? So these are all very important and useful, right? But now, suppose you have a developer and deploy such a pipeline, right? And throughout the test, right, you found that your final end, your ML-based applications, your prediction performance or whatever other performance is not good, right? Then how do we detect which components are in charge of those errors, right? Remember, each of this component could be machine learning driven, right? How do you do the poster stemming? How do you extract useful words, right? It could be some machine learning model. And how do you do past speech of tagging? That's about sequence prediction, right? You might use RNN, you might use transformers, you might use whatever other models, right? And doing parsing trees, that may be other models, right? So that means each machine learning model has their own errors, right? And your final performance actually is determined by their combination effects, right? Then once you have some error, right, how do we quantify or analyze how much each of these components contribute to the error, to the final prediction, right? So one commonly used approach is to gradually plug into the ground truth for the intermediate components and see how much accuracy of the final system changes. For example, if we plug in all the ground truths in every component, my accuracy should be 100, right? So now, if I only have like ground truths for text, words, part of speeching, and yeah, up to here, right? And now I run my machine learning model for parse trees, right? Oh, sorry. I have a ground truth for words, part of speeching, and parsing trees, right? And I use my machine learning based model, right? And now my accuracy drops to 89% accuracy, right? So this sounds reasonable. You kind of expect your machine learning model to give you 100% accuracy, right? So now, if we replace the ground truth in this component by using our parsing tree model, right? Maybe some other artificial neural nets, right? Then my accuracy reduced to 84%, right? That's reasonable. Your parsing tree component contributes like 5% error, right? Now, you further replace the part of speech tagging, right? By your model, by your RN, by your transformers, you find that your accuracy drops to 60%. Right? That's a giant drop, right? And then if you replace the words processing by the original component, you got a final end-to-end prediction is 55%, which we know that won't be satisfactory. Right? So now throughout this change of the accuracies, what can we conclude? Which component is problematic? Part of speeching, right? So because 8, with incorporation of this ground truth parts of speeching, if you plug in your ground your part of speeching tagging, it kind of reduce your accuracy from 84 to 60%, right? So that's why we have to substantially improve your part of speeching model to lift up the performance. That's just the one way, right? So in practice, you'll need to do ablation study. Right? Ablation study means that, okay, you keep all the other components the same, but you vary one single component and say what is going on, right? And that will make you be clear about what's the role, what's the importance, and what's the performance of each single component. Then you can make a strategies to improve them, right? This is particularly useful for feature engineering, right? So I have a collection. Suppose we have 1 million features, right? And by the way, we know that we only have a collection of features are doing well, and but we don't know which collection are, right? So we can evaluate a simpler system that progressively use fewer and fewer features and see which features gives the highest boost. Right? That's actually the same procedure as we, as in this example we have discussed. Right? So to summarize, it is not enough to have a classifier that works, right? It is useful to know why it works. Right? This is actually the secret, the business secret of those big companies, right? So for example, for OpenAI, they won't disclose how they're going to train their chat GPT model, right? Although there are many open source alternatives, and Google and Meta released their chatbot as well, right? Everybody knows that they're training the same model, which is called transformers, right? The architecture of the models was published 10 years ago, right? But how do you train them? How do you train them on how do you collect the data set? How do you process the data set? How do you pipeline the training procedure, right? Those are their top secrets, right? And actually, it is those procedures which determine the final performance. Okay, the last thing we want to talk about is how do we, in practice, inject machine learning into your task, right? Again, we want to discuss throughout a concrete example. Say you want to build a classifier that identifies whether a real physical fish is salmon or tuna, right? How do you go about this? We might have 2 strategies, right? The first strategy is more like academic strategy, which we call it slow approach. How can we do that? We carefully identify features, get the best data, clean noise, and whatever, to do a lot of transformations, all kind of stuff, right? Then we design a software architecture and maybe design a new learning algorithm, and then we implement and hope it works, right? So this procedure may take you 3 months until you get your first version, right? But your first version might work pretty well or reasonably well, like. So doing research, this is a good choice, right? Because you're trying to carefully design every step, right? And then combine them together. But in practice, this is often not favored. Like, for example, if your boss tell you, okay, I want to build a classifier, fish classifier, and for the use of people who are doing fishing, right? I have a we have hardware there, right? What we do is just implement or build out a fish classifier doing this. We then flash your classifier into our device, right? And we can use that, right? And I want that to be ready for next week. Right? So if you say, okay, I cannot finish that task, I can only deliver first version after 3 months, well, perhaps you'll get fired, right? You'll find someone other one to do this. Why? Because in practice, people want you to give some quick results first. Even at the beginning, that results are not good enough. For example, my classification error might be only 60% at the beginning. But as long as it can be used, you can use that first. That's why in the practice, right? People often choose the so-called hackers approach. We're going to first implement something and do a fast deployment. And then through a deployment, we'll find problems. Then we use the diagnostic error analysis tricks all we have discussed to find out problems and to iteratively improving this. That's why you see it's like how people are developing software, apps, and hardwares. Like we know iPhone 1.0, iPhone 2.0, iPhone 3.0, right? Every iteration, they earn a lot of money and use this money to invest for the next iteration, right? And it's not saying like every iteration is perfect. Actually, it's not perfect at all, right? They're always trying to improve. That's how in practice, if you want to be a machine learning engineering, what kind of style you should choose, right? You should do the hacker's approach, right? Do not be a careful researcher. Right? That won't catch up the pace of the applications. Right? So the advantage of doing this is that you can do the faster release, right? You can satisfy users' need. I mean, in some degree, right? And then through the updating and iterative procedure, you can get better and better solutions. Throughout the practice of machine learning, right, you should always watch out the right evaluation metric. Right? As we mentioned, in many applications, simple prediction accuracy might not be sufficient. Right? For example, in the recommendation, you might not always want to say that the prediction accuracy of the click. Right? You might also want to measure like whether a user really like your recommendations. Right? And how do you see that? Right? And for example, you might not always try to predict something old to the users, right? You might want to predict something refreshed, something new, right? Something the users have never seen and recommend such kind of products, right? And then the problem is that how do you measure the freshness of your product and the users, whether the users are in favor of that fresh products. Those are all like highly problematic, problem dependent and application dependent. And there's no unified formula to tell you how to measure this, right? You have to come out this measurement by yourself. Okay. Also be aware of contamination, right? Ensure that your training data is not contaminated with test set, right? Because learning is to generalize to new examples, right? So that's why every time we say, okay, your performance is very, very good, do not celebrate. Just first sit down, carefully check whether you kind of overlap your training and test data sets. Be aware of bias and variance trade-off. That means you should be aware of the bias between overfitting and underfitting. If you have a huge amount of data, then you might not be worried about the model complexity. Like in large language models, you have extract almost all the documents, codes, data from the word from the internet, right? You're going to worry about the model. Right? You're going to worry about, okay, I got 2 billion parameters here in my word. What if my model overfit? Model won't overfit because the data is different. be aware that intuitions may not work in high dimensions. That's true because in real world, we often have to deal with high dimensional feature vectors, right? And it cannot be pictured. There's no proof of picture. You have a curse of dimensionality issues, right? So don't trust too much about intuitions. Let data speak. And third one, don't trust too much about theory. That's kind of interesting. Theory helps us to have a different understanding of the structure and behavior models, but in practice, you cannot use theory as a Bible. The reason that for complicated applications or problems in practice, no theory can tell you everything, right? Because almost all theories are making some kind of assumptions. Most of those assumptions are invalid for your particular applications. That's why you should trust more on experiments and data. Right? And theory can only point you a general direction. It cannot be a answer to every question. And big data is not sufficient because data cleaner is also important, right? That's why this is kind of like a secret of how OpenAI trains their ChatGPT, right? Because you know a lot of trash data, right? Noise data, and how do you clean them, right? How do you use part of them? How do you use high quality data? Right? Those are all important questions. Unfortunately, the textbook won't tell you how to do that. Those are secrets there of their company, right? Learning requires knowledge to guide the learner, right? Machine learning is not magic wand, right? You have to tune it, you have to inject your intuition, even sometimes hypotheses to try to improve that. It's a highly, it's like an art. It's not like you have some handbook, you can do everything right. It's not like art. You don't know, you won't know which component will work at which scenario, right? Even for people doing research like me, right? One particular design of the neural network works pretty well here, but then it's totally stuck. I totally failed at a different scenario. Right? So it is the experience is highly important. Right. So what kind of knowledge do you need to accumulate during your practice? Right. You should have some sense like which model is the right one for this task, linear models, decision trees, or neural networks, and so on. Right. Which learning algorithms will work better, right? And what kind of feature learning should we conduct, right? And implicitly, all those knowledge are reflecting the nature of the problem. And unfortunately, the nature of different problems can vary as well. That's why what I said, like the experience is important. You have to gain your experience through practice. Right? And miscellaneous advice, right? Learns a simpler model first, right? If nothing, at least they form a baseline that you can improve upon, right? Don't try to build up a 250 layers in neural network first, right? It is resource consuming, and you don't know whether your method is reliable or not, right? Start from simple model, right? And ensemble seems to work better, right? In some gossip released heard from the internet, like people are talking about how they train the large language models, right? OpenAI, because it's said to use the so-called like mixture of expert model. The mixture of expert model is actually ensemble model, like proposed like 20 years ago. Like, and think about whether your problem is learnable at all. Of course, this is kind of a more fundamental, right? If you decide to apply machine learning to your particular problem, you need to think about, okay, if machine learning is the right way of doing it. Okay, I think that's all we have today. And I know that everyone is making a lot of time efforts for this class, and hopefully it worth your efforts. And I wish all of you have a great success in the future. Okay, let's stop here today.